One of the weirdest things about matrices is the way that the multiplication works is one of the first times that I ever encountered in mathematics where it wasn't commutative. That is a whole bunch of jargon to folks who don't use the word commutative a lot of the time, so let me show you what I mean. In every other component of math that I had experienced to this point, 3 times 2 was the same as 2 times 3, like both of them equal 6. But matrix multiplication is slightly different, and you might even be able to infer that based on what you've done so far. You've already seen situations where we have two matrices, and so the first one governs rows, and the second one governs columns, and that's just been our habit. So what that means is that A times B will almost never be the exact same thing as B times A, because in this one, A is governing rows, B is governing columns, and in this one they have the opposite roles. So this then leads to a fascinating scenario where sometimes not only are these two things not the same, but in fact sometimes like one of them doesn't even exist while the other one is perfectly normal. Let's prove this and see what this looks like. We'll start with A times B. So if we take A times B, we have 1, 2, 3, 4, and 5, and 7. This means that this is going to have 1, 2 rows, and it's going to have just one column, because this governs rows, and that governs columns. There are 2 rows here, there's only one column here. So I already know that my finished matrix will have 2 rows, and only one column. The row 1, column 1, row 2, column 1, and that's it. So first space of the two things that I'm looking for is governed by row 1, column 1. So that's 1 times 5 plus 2 times 7 is 14. And row 2, column 1, 3 times 5 is 15, 4 times 7, 7, 14, 21, 28. I've actually seen both of these numbers already tonight, so 5 plus 14 is 19, and 15 plus 28 should be 43. Vote the video down if it's not. Cool, so we have our 2-item matrix. It's very small, but it's exactly what we expected because the first matrix said we'd have 2 rows, second matrix said we'd have 1 column, and that's what we found. Now, let's take this same idea and try to find the reverse. So this was A times B. Now let's go back and try to find B times A. B times A would be 5, 7 times 1, 2, 3, 4. All right, so based on this, I'm expecting to see 2 rows, because this has 2 rows in it, 1, 2, and I'm also expecting to see 2 columns in my final answer. So that's a 2 by 2 matrix. It's going to have 1, 2, 3, 4 different items in it. So for this first place, this is row 1, column 1, row 1, column 2, row 2, column 1, and row 2, column 2. All right, so row 1, column 1, I'll take this 5, and I'll do column 1, 1, and 3. Okay, so it's 5 times 1, which is 5, plus... I don't have a different number to multiply by 3. Normally, there'd be 2 across and 2 here, so I would do the first one times the first one and the second one times the second one and add those together. I don't have that. So I'm missing the information that I would need for that piece. So the system that we defined as matrix multiplication already it's not working for my first term. I can keep going and see what happens. So this one would be row 2, column 2, so that'd be 5 times 2, which is 10, plus, but again, I need another number next to the 5 to multiply by the 4, and I don't have it. And this problem that we're encountering right now, we're going to encounter in every single space. There just isn't enough information in the first matrix to fill out what we need in our 2 by 2. That's bizarre, and it takes a while to figure out what the pattern is, so I will just cut straight to the chase. If you look closely at these, you can define them as rows by columns. So A has 2 rows by 2 columns. It's a 2 by 2 matrix. B has 2 rows and only 1 column. It's a 2 by 1 matrix. I'm going to erase what's on the board, so pause the video if you need it. And I'm going to show you the way that mathematicians think through whether or not matrix multiplication is possible for anything. The first problem we did was A times B. So we took a 2 by 2 matrix and we multiplied it by a 2 by 1 matrix. And our ending result, our product for that whole thing, you may remember, was a, was it 2 rows, 1 column? So it was a 2 by 1 matrix. Okay, cool. Then the second thing that we tried was a 2 by 1 matrix, B, and we took that one times the 2 by 2 matrix, and the whole thing just wasn't even possible. We got a big old frowny face. Here is the pattern that mathematicians use to figure out whether it will be possible. They look at the middle two terms right here. And in this case, you can see that the number of columns of the first one and the number of rows of the second one, they match up. And because they are the same, that means there's going to be enough information for every single item to have like a partner, a corresponding piece as you go through and try to fill out the rows. And that means that this is going to work. But if the two middle terms right here in the dimensions of the matrix don't match up, and in this case they don't, then you're not going to be able to multiply them at all. The process of multiplication is undefined for a matrix of that size. The other cool thing that you might notice is you can see that the two pieces we didn't use, from here to here, 2 by 1, is the dimension of the resulting matrix. And so you can tell whether it's possible by looking at the two middle terms, and you can tell what the size the result will be based on looking at the two outer terms, which is something you've already been doing in your matrix multiplication problems. This is just a different way of doing it. Long video, kind of boring. I apologize. It's going to be okay.